So far in this class, we've been focusing on using the stoichiometry roadmap, and really all the stoichiometry conversions we've been doing is we've been starting in a mass of a certain substance, let's just call that X, and we've been converting and trying to figure out, given an equation, like let's say this one down here, if I had a mass of hydrogen, what mass of water could I make with, let's say, 2 moles of hydrogen? So what we've been doing is going from a mass of X into moles of X, which would be the hydrogen, into moles of the other substance, which in my example would be something like the water here, and then into a mass of water. But what if I asked you to convert into something other than mass of the other substance? What if I asked you to find, if I gave you 2 grams of hydrogen, how many atoms or particles of water would that make? This would require a different path than our gram to gram path that we've talked about previously, where we're just kind of going across this mole map. So this is called a Stoich level 1.5 worksheet because it's not anything super different than what you've been doing. It is just a new stoichiometry pathway that we haven't explored before. So the same skills of factor label are going to apply. We're just going to use a different conversion factor from our moles chapter called Avogadro's number to figure out how many particles of our substance we're looking for. Conversely, we might also ask you to start in particles of a substance and figure out how many grams of the other substance that's equal to. So we'll go through 2 examples to show you how do you use Avogadro's number, or 6.02 times 10 to the 23rd, to do some stoichiometry conversions. So, example number 1 is going to be how many molecules of water are formed when 25 grams of hydrogen are burned in excess oxygen in the following equation. This word excess just means that there is a whole bunch of oxygen here, so that we're going to make all of our potential product of water here. Okay. All right, let's take a look at what our unknown is and what we are looking for. How many molecules of H2O? Let's call that our unknown. So I'm going to go here and I'm going to put a question mark over this guy. We do not know how many molecules of H2O we have, but we are given that we want 25 grams of hydrogen. So that is our given here. So like any problem, we are going to start by identifying our unknown. Our unknown is going to be question mark, and I'm going to abbreviate molecules with MLLC. I suggest you do that. Otherwise, if you do mole, it looks a whole lot like a mole, but I'm going to do molic there to know it's molecules, is going to be equal to, let's put our given over 1. That's going to be our 25.0 grams of hydrogen. Now, hydrogen has the formula of H2, so I'm going to include that after this label. Next step, we are going to take a look at this mole map and see where we are. Well, we are in a mass of X here. In order for us to get to our end goal, which is going to be particles or molecules of water, that would fall under the category of our particle here, we know that our next jump is going to be to moles of X. So when in doubt, go to moles in a stoichiometry problem. Let's go ahead and do that. Looking at the molar mass of hydrogen, at this point, you may have this memorized, but hydrogen has a mass of 1.008 grams per mole. I'm going to go out to 2 decimals and round this to 1.01. So we're going to say that for every 1 mole of hydrogen, since there are 2 hydrogens, 1.01 times 2 is about 2.02. And that will be 2.02 grams of hydrogen. So I just doubled that molar mass for hydrogen there. Grams of H2, cancel. Next step, we are now in moles of X. We need to get to particles of Y, so the next step is a mole to mole ratio. Let's take a look at our balanced equation in order to solve that mole to mole ratio. In front of the H2, I see that there is a 2 though, 2 there. So that means that for every 2 moles of H2, I also have 2 moles of H2O. In this case, our mole to mole ratio is 2 to 2, which may seem a little strange given what you've done in fractions in math class. You would normally reduce that to 1 over 1. Even when the coefficients are the same, we still need to include the mole-to-mole ratio. Moles of H2 have gone ahead and canceled. Now that we are in moles of Y, which would be our moles of H2O, this question asks for how many molecules of H2O you have. You may be tempted to use now a molar mass of water to find a mass of water, but if I look at the problem, did the problem ask us to find a mass of water? The answer you should have is absolutely not. My next fraction, therefore, should be a fraction that takes me from moles of water into particles of water. Well, recall from the mole unit that for every 1 mole of a substance, in this case we have water, we have 6.02 times 10 to the 23rd atoms, molecules, particles, whatever that is, there. In this case, we're talking about a molecule, so we're going to use molecules. Moles of H2O are going to cancel. I am left with molecules of H2O on the top of this fraction. Since we are left with the unit we wanted in the very beginning, my conversions are done here. Looking at how we go ahead and do the math on this problem, we're going to go 25 times 1 times 2, multiply all of our top numbers. And now Avogadro's number, recall when we put this in the calculator, it's really, really important that we use that double E button. So to engage that double E button, I'm going to press second, comma, and you're going to see an E appear there. And then I'm going to put the exponent of 23 right after that E. Notice how there's no times 10. I'm literally just putting the number out in front of the times 10, 6.02, and then the exponent number after the E there. I'm going to press enter, and I'm going to get a really large number. That's why you're seeing E to the 25th there. I'm going to divide by, in parentheses, 1 times 2.02 times 2 times, I believe that's a 1 at the end. What we are going to get as a result is this answer of 7.45049 E24. I'm just going to go ahead and write down the first few decimals to that. Since our given number had 1, 2, 3 sig figs, I am going to round this number off to 3 sig figs. So I'm going to make it 7.45 since there is a 0 after that 45 there. E to the 24th just means times 10 to the 24th. And don't forget your units. So we're going to go molecules of H2O. And that is your final answer for example number 1. Let's go ahead and do the next example on this worksheet. This example says if 1.204 times 10 to the 24th atoms of copper are formed by a single replacement reaction of aluminum and copper 2 chloride, how many grams of aluminum must have been used? In this case, we are given, as our given, 1.204 times 10 to the 24th atoms of copper. Our given value, unlike the first question where we were given grams, is now going to be atoms. So we're kind of flipping the order of the previous problem, and we're going to be starting in particles of X in this particular problem. That in this case would be atoms of Cu. Where's the endpoint? It says we're looking for how many grams of aluminum must have been used in this reaction if we added that 1.204 times 10 to the 24th atoms of copper. So our unknown is a mass of aluminum. On the Stoich map, that corresponds to our mass of Y. What's the path we're going to have to take here? Well, it's going to be a 1, 2, 3 fractions after the given that we should see there. But it's almost the reverse of what we just did in the previous problem, where we went from particles or mass to particles. Let's go ahead and set this up. Question mark, grams of aluminum. It's going to be equal to our 1.204 times 10 to the 24th atoms of Cu. Let's go ahead and put that over 1. Now, step number 1, given the map, is we're in particles, or atoms of Cu. We need to get to moles. We are going to use Avogadro's number to do that. Recall that Avogadro's number applies to atoms, particles, formula units, and molecules. So it is totally legal to use Avogadro's number here and say that for every 1 mole of Cu, we have 6.02 times 10 to the 23rd atoms of Cu. Since copper is an element, that's why we're using atoms there. In the previous example, water is a molecule. That's why we used molecules in Avogadro's number. Now we are in moles of copper. We are looking to get to grams of substance Y, the other substance. To get to grams of aluminum, we are currently in moles of X. We got to use our mole to mole ratio to get to moles of aluminum, or moles of Y. That will require a mole to mole ratio. For every 3 moles of copper, as highlighted in copper's coefficient here, we are going to require 2 moles of aluminum. Moles of copper cancel. And now we are in moles of aluminum, which corresponds to moles of Y. Final step should seem pretty familiar. We need to go ahead and use a molar mass of Y to get from moles of aluminum to grams of aluminum. For every 1 mole of aluminum, we need to find how many grams that is, so let me go ahead and consult our periodic table. 1 mole of aluminum weighs 26.982 grams. We're going to go ahead and pull those first 2 decimals, the 26 and the 9 and the 8. Moles of aluminum cancel. Let's go ahead and evaluate. Are we left with the unit we want? The unit that we are looking for was mass of Y, or grams of aluminum. It appears as if we are left with that proper unit. Let's do the math. 1.204, second, comma button to get that double E on this calculator, 24 times 1 times, I believe that is a 2, times the molar mass of aluminum, which was 26.98. You have those big numbers there as your answer because we multiplied by a very large quantity as our given. We're going to divide by 1 times, now Avogadro's number, 6.02, second E to the 23rd. Multiply this, and again, we're in parentheses here to keep our order of operations correct, times 3, times 1. And what we're left with is 35.973 grams of aluminum. Now I pulled a few extra decimals on this one so we can evaluate our sig figs here. I always tell students to go off of the given value for our sig figs. The given value is in scientific notation. We need to then count this first number for sig figs. 1 and 2 are definitely sig figs. This 0 is sandwiched between the 2 and the 4, making it also a sig fig. And then the 4 being a non-zero digit is also a sig fig. We have, therefore, 4 sig figs. And we're going to then round our answer to 4 sig figs. 1, 2, 3, 4, all non-zero digits. There is a 3 past the chopping block there. That means we are not going to round the 7 up. So after sig fig rounding, our final answer is 35.97 grams of aluminum. Hopefully this helps get you started on the other problems. You will find that all the other problems on this worksheet aren't anything super different than what we did. But you will find that you're going to go through different pathways on this mole map involving this new conversion of Avogadro's number. Hopefully that helps.